I'd like to explain to you what atomic radius is, and then review period trends for atomic radius. That is to say, what does the atomic radius of elements do traveling across a period? Is there patterns in that? And then also, in a group of elements, is there a trend in atomic radius? So atomic radius is defined as 1/2 the distance between two identical nuclei. So if you think of an atom like a sphere, then the atomic radius is from here to here. Okay, okay, and that's pretty straightforward. Um, so what determines the atomic radius is pretty simple. Um, just remember, protons attract electrons. So if you think about protons, the nucleus as being a positive, out there are negatives that take up the rest of the atom, and that more protons means more positive charge, and and the further away from the nucleus electrons are, the less tightly they'll be held. Then you can pretty much rationalize these period and group trends. So let's look at the period trend first. Okay, I've got some pre-drawn atoms here. We're going to use like Bohr models of the atom, just even though we know that electrons in atoms are in s, p, d's, and f orbitals. Um, we're going to use these models just for simplicity's sake, because they do work for this. Okay, so let's look at period 2. So let's say that we have lithium here, right here, and we know it's 1s2, 2s1. Okay, so we've got two electrons in a 1s, whatever that looks like. It's a sphere, right? And then we've got um, one in the 2s. And we're just focusing on valence electrons now, so don't get too hung up about that. We have, in lithium, we have 3 protons and 3 electrons. All right? Now, 3 protons are attracting these 3 electrons, and one of the 3 electrons is in n equals 2, or the second energy level, the second principal quantum number, okay? And that's the valence electron. And that electron is further from the nucleus than the other 2 because it's in a higher n, which is further away, and it's also shielded from the 3 protons. Remember, there's 3 protons in here that are pulling the electrons toward it. These 2 inner core electrons right here shield the third electron, the valence electron, from the nuclear pull. Now, this shielding effect really just depends on how many inner core electrons there are. And so every element in the second period is going to have 2 inner core electrons. That's important. So shielding pretty much remains constant across a group, this shielding effect. So shielding is roughly constant as you're traveling from left to right, because every element as you travel across the period is going to have the same number of inner core electrons. In this case, in period 2, we're going to have 2. So let's look at the next element. We got beryllium. Beryllium is 1s2, 2s2. So now we've got 2 inner core electrons, same, so shielding's roughly the same. But now we have 2 valence electrons. You might say, well, there's 2 electrons, that maybe that's bigger. Well, not really. Actually, remember, we've got in this atom, in this beryllium atom, we now have 4 protons, and 1 additional proton than before, and we have 4 electrons. But since shielding stays roughly the same because there's 2 inner core electrons, just like lithium, what happens is beryllium's 4 protons cause this to shrink down a bit. And so beryllium is smaller than lithium. So I'm going to put that here. Okay? I just wiped out my electron configuration. Okay, now boron, 1s2, 2s2, 2p1. We've got 3 valence electrons, right? The 2s and the 2p are 3 valence electrons. And remember, we're using this kind of simplified Bohr model because it works for this explanation. We know that it's not like that. We know that the S and P are not equal in energy, and putting them on the same line is really not quite right. But we know that they're more similar in energy to each other than they are the 1s. And that really is what matters right now. So, in this case, we've got 2 inner core electrons. And so shielding is the same as before. And now we've got 3 electrons, 3 valence electrons here. 1, 2, 3. And because we have now 5 protons in the nucleus, that's going to attract those valence electrons even more strongly than before. So this is even going to be a smaller atom than beryllium. Make it nice and small. And this is the period trend. Move this guy over here, this guy over here, and this guy over here. So that's the period trend. Okay? As you go from the left side to the right side, shielding remains constant, but nuclear charge increases. That's the number of protons. So the valence electrons are pulled closer to the nucleus. Okay? And if we get all the way to fluorine, which has an electron configuration of 1s2, 2s2, 2p5, we see that the atomic radius has really shrunk down. Okay? Because you have now you have 9 protons, but the shielding is roughly the same from those 2 inner core electrons, and so those 7 valence electrons are really going to experience a stronger attractive force. And if we look at the actual sizes of these atoms, that lithium is 152 picometers, beryllium's 112, boron 88, fluorine all the way across 68. So it really does, atomic radius really decreases from left to right. But it's not good enough to just say atomic radius decreases left to right, because it does. Atomic radius decreases from left to right because the number of inner core electrons is constant. So shielding is constant, or roughly constant. But nuclear charge increases because the atomic number, or the number of protons, increases from left to right. Lithium has 3 protons, beryllium has 4, boron has 5, carbon has 6. So the nuclear charges keeps increasing, and so those valence electrons get attracted more with each subsequent addition of a proton. And so elements at the left tend to be very large compared to elements at the right of a period. Now, what about the other factor? The other factor is shielding and principal quantum number. So So we've talked already about shielding being constant across a period. Okay, let's look at about the group trend. So let's look at the group trend. And let's look at the alkali metals. Again, lithium, 1s2, 2s1. And then let's look at the next one down is sodium. Which is 1s2, 2s2, 2p6, 3s1. Okay, so you might say, well, sodium has 11 protons and 11 electrons, so why isn't that smaller? Because lithium only has 3 protons and 3 electrons. And the answer is it's not just nuclear charge that affects the atom size. In this case, we talk about what is the valence electron, what's the principal quantum number of the valence electron. Okay, lithium valence electron is in n equals 2. It experienced that electron, this electron here, experiences shielding from 2 inner core electrons. Sodium's valence electrons in n equals 3, which we know is further from the nucleus than n equals 2. It's shielded from the nuclear pole. Remember, it's getting pulled to the center by these protons here, 11 protons here. It's getting shielded by 10 inner core electrons. Okay, remember, these guys are all negative. And so when you have more negatives kind of shielding this negative, remember the negatives do repel each other too, shielding that electron from the nucleus, that it's further away. And so what you see is generally atomic radius increases down the group. And that is because shielding increases down the group, and the valence electrons are in a higher principal quantum number. So there's more inner core electrons, that valence electron is more shielded. So to summarize here. What determines atomic radius? The group trend. Okay? Electrons with higher n are located further from the nucleus than those with lower n. So this is the second scenario. That's the group trend. So these electrons are also shielded from the positive nucleus by more inner core electrons. So elements at the bottom are larger, and atoms atomic radius at the top of a group are smaller. Okay, and the period trend. Okay, in a period, each subsequent element has an additional proton and an additional electron. So you gain a proton and an electron for each element, for the next element. The additional electron remains in the same energy level or the same principal quantum number. Okay, so it experiences similar shielding from the nucleus from the electron before. So we said that, like boron, 1s2, 2s2, 2p1, every electron that you're adding across that second period is in n equals 2. There's 2 inner core electrons. So it experiences the same shielding from the nucleus. The additional proton, as you move from left to right, increases the nuclear charge, so the valence electrons are pulled a little closer to the nucleus. So bottom line is, the trend is larger atoms on the left side of a period to smaller on the right. You might want to, at this stage of your studies, say, well, who cares how big the atom is? It really has, remember, chemistry is all about electrons. And so if you can predict how these electrons are going to behave, like whether or not it's easy for an atom to lose one, and as you might guess, larger atoms with valence electrons that are further from the nucleus, probably more likely to give them up. That it really sort of gives you an insight to the behavior of these elements, and you might recognize that smaller atoms at the right side of the table will tend to be able to attract electrons to the nucleus better because their valence electrons are closer to that center of positive charge that is the nucleus. So what you find is the elements on the right-hand side are really capable of competing for electrons or even like ripping them off of other elements, and that elements on the left-hand side, where they're very large and the electrons are far away from the nucleus, tend to give those valence electrons up and become positive ions. So the period and the group trends for atomic radius really matter because they give you insight into predicting chemical behavior, and then your chemistry class becomes less memorization and more intuitive. I hope this helped.